Welcome back, Physics 181. We're talking about temperature and heat. We talked about temperature in the last video. Now I really want to talk about heat really quickly, just to distinguish it from temperature. Here it is. It's the transfer of energy across a boundary of a system, so out of or into a particular system or object, due to a difference in temperature between the system and other things which it has thermal contact with, other objects, its surroundings, etc. That's really so notice transfer of energy. That means heat has units of energy, joules for us. We're going to measure heat in joules. We also use this term to represent that amount of energy being transferred, or maybe amount of energy subject to being transferred. Really quickly, so kind of synonymous, but heat is energy. Energy that is moving between objects of different temperature, or about to move, or has just barely moved, or something like that, right? The other thing to keep in mind about this, heat and temperature are different quantities. Obviously, heat is measured in units of energy, temperature has its own units, Kelvin, fundamental, right? But there's also this thing called internal energy. That internal energy can be associated with temperature. The details of which we're going to talk about in the kinetic theory of gases in Chapter 2. But internal energy, also energy, but distinctly different from heat. Internal energy is in an object, not energy being transferred between an object and its surroundings or some other object. So keep those in mind. Heat is thermal energy moving place to place, or having just moved or about to move. Internal energy is stuck inside of a system, inside of an object. Temperature is associated with internal energy, related to heat through the zeroth law, but really a measure of average molecular motion, right? Now remember that temperature being an average molecular motion, that leads us to this idea. So think of a solid in particular as a bunch of molecules or atoms connected by little springs. So the springs can flex as these atoms or molecules kind of jiggle around, right? But the higher the temperature, the more they jiggle around. And you can figure if all the atoms in an object jiggle around a little bit more, that object's going to be bigger in its bulk material, right? So in a positive change in temperature would increase the dimensions of a solid object. Really what I want you guys to know is these rules for thermal expansion. There's linear thermal expansion, surface or area thermal expansion, and volume or volumetric or bulk 3D thermal expansion. We look at these and notice that I have delta L, delta A, delta V. Those are all changes in. So let's look at the simplest one, the thermal expansion of length. A change in the length equals alpha, some coefficient. These are found in table 1.2 in the textbook. There's a link right there. And look at table 1.2 in our text. The ones that we might use, I will give them to you in test problems and such, but some of the book problems, you may have to look these things up. And you can, of course, always ask Google about the coefficient of thermal expansion, right? Linear expansion, probably. But that coefficient times the length, L is whatever the original length was, right? At some original temperature, and by how much its temperature changed, delta T. Remember that delta means a change in. Changes in length are from changes in temperature. So I could really rewrite this as L, L final minus L initial equals alpha L initial times T final minus T initial. That's a little bit of a long way to get to the same expression. So we've taken the changes in and we're really interested in the change anyway. But if I need to take the change in either the temperature or the length and figure out what's the total final length, I need to know what the original length and temperature were as well, right? So things can expand just linearly with this coefficient alpha. We can look those up. For areas, I get two linear expansions, right? One along the length, one along the width. So I do 2 times alpha. and I still use a change in area from the original area, right? Volume, 3 times alpha, length, width, height, right? But very often this 3 times alpha gets wrapped up into a single volumetric coefficient of expansion, and we just call it beta. So beta values for beta are in table 1.2 as well. It can be the case in some very weird materials that beta is not equal to 3 alpha. Most solids, this is true, but not all solids. Some expand differently along different planes, particularly very specially engineered crystalline materials can expand more along one dimension than another. And we're finding more of those all the time, and they're really interesting classes of materials. But for our general case, beta equals 3 alphas. Close enough. But if you see an exemption to that, take the beta value as the value for expansion, because it may be that on average it doesn't expand the same in all directions. And that's why sometimes we might have to take that 3 alpha and figure out things separately. We're not going to do any of that in our class. We'll stick with these formulas and the application of them for thermal expansion. That's really what I want you to know for thermal expansion, how to use these formulas to figure out things like the bridge expands, right? You see a bridge expansion joint in picture A for the bridge shown in picture B there. And you see these, particularly around here, it's important around in Nevada because it gets pretty hot in the summer and pretty cold in the winter. And the length of that bridge is really actually changing. And we need to know by how much so that we can put some expansion contraction joints in there so the road doesn't buckle, right? Anyway, let's move on. The next thing we want to talk about is this specific heat, aka the specific heat capacity. It's really truly the specific heat capacity, but 9 times out of 10, scientists just call it the specific heat. It's a capacity per unit mass. The specific heat, little c. If you see a big C, that's probably specific heat capacity, not per unit mass. That's a different value that does not include this mass term, but we're going to just use little c. And its definition is given here. Heat Q divided by mass times delta T, right? If energy Q transfers to a substance of mass M, the temperature changes by delta T, then the specific heat is that. The much more useful form of this is to rearrange it and say the amount of energy going in or out, positive if it goes in, negative if it goes out, the amount of heat energy Q, capital Q is going to be our variable name for heat energy, equals MC delta T. Some people, particularly they're studying physics so they can get into med school, remember this is the MCAT equation, even though delta is not an A. Whatever. M is mass of the substance in kilograms. C is a material property that we're going to look up. There's tables and tables all over the place. You can ask for the specific heat of things from Google and it'll tell you. They're in chapter 1. There's a table of specific heats of materials that we'll need. Sometimes we'll find it, sometimes we'll be given it and need to use it. Delta T, a change in temperature. Because this is a change in temperature, we can put in a number of degrees Celsius or a number of Kelvin and we'll get the same thing, right? Adding 10 degrees Celsius is the same as adding 10 Kelvin. But remember that delta T could be written as a T final minus T initial. And so if delta T is positive, that must be due to heat coming in, positive amount of heat coming in. If delta T is negative, heat's going out. And we can use this from the definition of specific heat capacity. We can use this formula Q equals MC delta T to figure out a lot of stuff and do some really cool experiments as well. There's some specific heat values from the table in the book. I look at concrete or granite on average. These vary by formulation, of course. The human body has an average specific heat about 3,500 joules per kilogram degree Celsius, or that could be a joules per kilogram Kelvin. Same thing, same number, right? Notice that air and steam, these gases, have different specific heats. The specific heat in parentheses is the specific heat at constant pressure. That's probably the one we'll use for gases if we're talking about I've got some steam and I'm cooling it off and it condenses into a cup or something. The one that's not in parentheses is for the gas at constant volume. That's if I have a sealed up container that doesn't allow the volume of the steam to change, or the air, or whatever gas I'm talking about. Notice here the specific heat of water. And it says at 15 degrees C, right? 4,186. It changes by almost nothing in the entire range of temperatures where H2O is liquid water. So the specific heat of water is pretty big, 4,186. That's one of the biggest specific heats you see. Look down at ice further in the 2090, right? Much smaller. And even though it's the same molecules, they're just bound together in a different way, different state of matter, right? Water has one of the highest specific heats, and this comes into play for lots of things. Water having a high specific heat is the reason we use water and other similar things for heating, cooling, exchanges, and all that kind of stuff. It also has some other desirable properties for using it, and it's commonly available, right? So keep in mind these specific heat values as we talk about it, and use this table, and feel free to look up stuff online and just be sure you say this is the specific heat value I'm using for this particular substance when you're working problems. Even just say, C for water is 4,186 joules per kilogram Kelvin, and that's the one I'm using, right? Just be clear about that when you're working out problems. And that way, if you've used, particularly with gases, if you've used one at constant pressure and you should use one at constant volume, you can figure it out pretty quick, right? Very strictly speaking, that specific heat, C, actually varies with temperature. Like I said, for water, there's not quite a 1% variation in its specific heat value between 0 and 100 degrees C. All the temperatures at which you'd have liquid water. Very strictly speaking, the correct equation is an integral equation, integral of C times dt from initial temperature to final temperature. We'd have to have a functional form for C, the specific heat, for this to work for us. We're not going to do this much. Because the variations are pretty small over the temperature ranges we're going to look at, we're just going to say, yeah, C is a constant. It's a material constant for us. It is close enough. We're going to neglect those variations unless we're very specifically state otherwise. And if I do specifically state otherwise, I'll give you some sort of functional form for C. C varies with temperature as the square of temperature times a constant or something like that, right? So you'll know how to handle that. You can plug it back into this integral and do some simple integrals. But most of the time we just ignore those variations because they're small enough that ignoring them is fine. I'm going to stop here, and we're going to come back and talk in the next video. We'll talk about an application of this for calorimetry. Calorimetry is measuring specific heat. It involves heating material, adding it to a sample of water where we know the specific heat, finding the final temperature. Sometimes we mix multiple materials and get really complicated with this calorimetry. But we're going to come back and talk more about how to do this calorimetry problem in the next video. I'll see you there.